Our first step is to start a new case, and here we have the Simulation Basis Manager page. So we're going to move here to the Fluid Packages tab and click on Add a Package. The package that we're going to use for this example is Uniquac, and if we look here on the binary coefficients, we want to check that Unifac VLE is selected. So we'll leave that one. Now we need to move to our components and add them from here. So the first one that we want to add is propylene oxide. Here. Second one is propylene glycol, and the third one is just water. So once we've added those components, we can close this little one. Now we need to go to reactions, and we need to add a reaction. So the type of reaction we're going to add is a kinetic reaction. And we click here on Add Reaction, and we're given the opportunity to put in the details for our kinetic reaction, Reaction 1. So the three components that we have are our propylene oxide, water, and propylene glycol, and we need to put in the stoichiometric coefficients for those. So those are -1 for propylene glycol, -1 for water, and +1 for propylene glycol. And if we look at our balance error, this should read 0, which means we've got a balanced chemical reaction. So if we look at the forward and reverse orders for the reaction here, we can change the forward order for water to 0 because water is in excess, and we can change the reverse order to 0 for all of these entries because we don't expect any reverse reaction to occur. If we look at our basis tab, we want to check that the basis is molar concentration and our base component is propylene oxide. If we look here at the reaction phase, we actually want to use combined liquid, and the minimum and maximum temperatures that we see there are fine. And the basis units, we want to check that it's kilogram mole per meter cubed and that the rate units are kilogram mole per cubic meter second. So that's all fine. If we move to the parameters tabs, we need to put in these parameters for the reaction, which come from the Arrhenius equation, which is described over here. So we have A is 4.722 by 10 to the power of 9, and E is 7.5 by 10 to the power of 4, and we can leave beta empty. We don't want to change these reverse reaction parameters, and this is pleasing to see. It says that our kinetic reaction, reaction 1, is ready. So that's all set up. We can close this, and we can close our little reactions box. So on our Simulation Basis Manager page, we need to, on our reaction set, we need to highlight this global reaction set, and we need to add that to our fluid package, and we click Add that set to the fluid package. This links our reaction to the fluid package that we selected earlier. So that's all done. We can enter our simulation environment. So the first thing we need to do is to add our cstr reactor, and then we're going to create a feed stream and 2 product streams. So you can do that by dragging these icons in, or we can take a shortcut and just type in our feed stream. So call this one reactor feed stream. To start with, and you can see that that's already appeared here. So if we double click on that, we want to set the stream temperature to 40 degrees Celsius and the pressure to 100 kilopascals. And if we move to the composition, we don't want to use mole fractions, we want to use mole flows as the basis here. So we click on basis, change this to mole flows. You'll see that that's updated there now. And the numbers that we're going to put in for propylene oxide is 70 kilogram moles per hour, and for water is 288 kilogram moles per hour. So we normalize that and click OK, and what that does is we'll enter 0 for propylene glycol. So what this tells us now, the reactor feed stream is fully defined, and so HYSYS can solve for it, and this bar here now is green and it says that it's OK. So we can close that. We've already connected these up, and we now need a liquid product stream. So we just type that in there and that will appear for us. And if we do the same for the vapor outlet, you'll see that our reactor vent stream is also created. Now, because there's an energy balance here, we need an energy stream. So we're going to call that coolant and add it like that. So here's that stream there, our coolant. And when we created this one, we should have set that the temperature was 40 degrees Celsius and pressure 100 kilopascals on that one. So now we need to tell the reactor what reaction is occurring. So if we double click on the reactor and move here to the reactions tab, our reaction set, the global reaction set, and there's only one reaction, which is reaction 1. We only defined one reaction at the beginning. If we move to our rating tab, the volume of our reactor is 7 cubic meters. And if we move here to the design tab, on parameters, the default for liquid volume is 50%. Liquid volume, we're going to change that to 100%. So we're saying that our cstr is fully filled with liquid. So back on our design tab here, instead of our default name, we're going to change that to reactor, and this says OK. So we're all done. So if we look now briefly at the example 4.5 from chapter 4 of the book, you can see that this can be used to check our hand calculation, which we did for a cstr. So if we look at the reactor vent stream to begin with, either by just holding the mouse here and observing that the molar flow is 0, or double clicking on this and looking at all of the stream properties and conditions, we can see that the molar flow is 0, mass flow is 0. So that tells us that there's nothing in the gas stream coming out of our reactor, and that everything is in the liquid. When we look here, we can probe the stream to see what is the composition. So if you compare these values here, you can see that they correspond to what's written there in the book. And if we look at the reactor itself, we can check to see what conversion we obtained. And the actual conversion that was solved for by HYSYS is 78.69%. So this compares very, very well to our hand calculation, where we found a conversion of 78.2%. It's only a very small difference, and that arises partly from the fact that in our hand calculations we assumed that there was no change in the liquid volumetric flow. So we assumed a constant density. There would be some slight change, and that's one of the reasons that a slight difference in the conversion is found here.